Hello, my name is Calin Adrian POPA. I'm from West University of Timișoara, Romania, and I'm going to present to you Mittag Leffler stability of neutral type fractional order neural networks with mixed delays. Although fractional calculus has been around for a long time, it was only recently applied to neural networks because of its intriguing qualities that give the system infinite memory, which is a desirable property for neural networks. As a result, fractional order neural networks have gotten a lot of attention in recent years. Because of the finite switching speed of the amplifiers, time delays are known to occur in electrical implementations of neural networks. The neural networks might become unstable and chaotic as a result of these time delay, and thus time delays are required in neural networks models. New and better models are produced on a regular basis, and fractional order time-delayed neural networks are undoubtedly one such model that has recently gained more academic attention. In this paper, we study the Mittag-Leffler stability of neutral type fractional order neural networks with mixed delays. The fractional order version of the Lyapunov direct method for Mittag-Leffler stability is used to derive the Mittag-Leffler stabilities for these networks. One highlight is the usage of the free weighing matrix approach among the first times in the context of fractional order neural networks, which significantly reduces the conservatism of the sufficient conditions. To demonstrate the theoretical result, one numerical example is offered. First, we discuss preliminaries about fractional calculus. So the fractional integral of order alpha for an integrable function x is defined in this way, where gamma is the gamma function, which is defined in this way. The fractional Caputo derivative of order alpha for function x is defined in this way, and for alpha between 0 and 1 it is defined in this way. The Mittag-Leffler function is defined in this way, and as you can see, for alpha equals 1, it is a generalization of the exponential function. The model discussed in this paper is defined in this way, where xi of t is the state of the ith neuron at time t, ci is the self-feedback weight for the ith neuron, aij is the weight without time delay between the ith and jth neurons, bij is the weight with time delay between ith and j neurons, gij is the distributed delay between the ith and jth neurons, hi is the neutral type weight of the ith neuron, fj are the nonlinear activation functions, ii is the external input for the ith neuron, tau are the time varying delays, eta is the distributed delay, theta is the neutral type delay. We assume that the time varying delays are continuously differentiable functions, and there exists tau and tau prime such that these conditions hold. We defined omega as being the maximum between tau, eta and theta. The initial conditions of system 1 are given in this way, and the norm defined on the space of all initial conditions is the supremum norm. We assume that system 1 has a unique equilibrium point, which is denoted by x star. So, denoting qi of t as xi of t minus xi star, system 1 becomes in this form, where fj bar are functions defined in this way. Correspondingly, the initial conditions or system of this system 2 are now given by in this way with sigma I of t belonging to the same set as phi I of t. And now we can write system 2 in matrix form in this way. We say that the equilibrium point x star of system 1 is Mittag-Leffler stable if there exist positive constants lambda and beta such that this inequality holds. The following assumption will be made about the activation functions, which represents the Lipschitz assumptions, where Lj are the Lipschitz constants, which we put in the capital L matrix. Now we will use in our proof the following lemmas. So this is a classical lemma used in fractional order system calculus. The second one is the Hallanay inequality for fractional order systems, and the last one is a classical inequality used in neural networks stability papers. Now the main result of our paper, for it we will assume that alpha is between 0 and 1, because lemmas 6 and 7 assume that alpha is between 0 and 1, and if also we have assumption 5, which is the Lipschitz conditions for the activation functions true, then the equilibrium point for system 1 is Mittag-Leffler stable if there exists positive definite matrix P, diagonal positive definite matrix R, any matrices n1 up until n6, and the positive number phi, such that this linear matrix inequality holds omega, where omega is given in by these elements. Now for the proof, we define the Lyapunov-like function v of t in this way, and taking the fractional order derivative of v of t along the trajectories of system 1 and using lemma 6, which is this one, we obtain this inequality. Now, by using the Lipschitz assumption, we obtain that there exists a positive definite diagonal matrix R such that this inequality holds. Now, from lemma 8, so from this lemma, used with Q equals to P inverse of P, these two inequalities are true. Then, using this inequality, these two, and also this one, we obtain this inequality. Okay, and now we use the free weighing matrix approach. So for any matrices n1 and 6, we have that this identity holds true. And now, by transposing identity 10 and adding both the original identity and its transpose to 9, so to this inequality, we obtain that this inequality holds, where psi of t is defined in this way and omega is defined in the statement of the theorem here. Because omega is assumed to be negative definite, we obtain this inequality, and by using lemma 7, so this lemma, the Hallanay inequality, we obtained this inequality, and this can be written equivalently in this way, and further equivalently in this way. And now we can see that by definition 4, so this definition, the equilibrium point of system 1 is Mittag-Leffler stable, thus ending the proof of the theorem. Now let's give a numerical example. Consider the fractional order neural network given in this way. Assume that it has a unique equilibrium point, which is denoted x star, and define qi of t as being xi of t minus xi star. Now system 11 becomes in this way, where fj bar is defined in this way. The parameters of the model are given in this way, so the C, A, B, G, age matrices, the activation functions, and also the time varying delays given in this way, the distributed delay 0.05 and the neutral type delay 0.08. So we have the theta and theta prime are 0.1 and omega is also 0.1. You can see that the activation functions satisfy the Lipschitz conditions, and the L matrix is given in this way. So it can be verified now that for phi equals 0.01 R given in this way, and the values of the other matrices are omitted for space considerations, the conditions in theorem 9, so these conditions are now satisfied. So this, based on this theorem, we conclude that the assumed unique equilibrium point of system 11 is Mittag-Leffler stable. So the state trajectories for state Q1 for 8 initial values is given in figure 1, and for state Q2 is given in figure 2 for 8 different initial values, which are depicted with different colors. So to conclude, one sufficient criterion which ensures the Mittag-Leffler stability of neutral type fractional order neural networks with mixed delays was given by making the assumption that the activation functions satisfy the Lipschitz conditions. The fractional order extensions of the Lyapunov direct method for Mittag-Leffler stabilities was used to realize the Mittag-Leffler stability of the introduced networks. The free weighing matrix approach was employed among the first times in the context of fractional order neural networks, which significantly reduced the conservatism of the sufficient criteria. The feasibility and the effectiveness of the theoretical results were illustrated by providing one numerical example. The introduced methods in the paper are general and can be used to obtain sufficient criteria for Mittag-Leffler stability of neural network models with impulsive effects, reaction diffusion terms, or Markovian jump parameters. These developments represent promising future work directions. Here are some references used in the paper, and thank you for your attention.